Good morning. Today we will talk about multi-layer neural network and the backpropagation algorithm. To refresh your memory, let us see what we can do by a single layer neural network. If we use a single layer perceptron, which we have already seen, in a single layer perceptron, we have a linear summation of the input units followed by a non-linear function, and the non-linear function in the case of a perceptron is a thresholding function, but we could also use other functions such as the sigmoid function, the tanh function or the ReLU function. So, we do sigma of sigma wxi if you are using the sigmoid function, or in general we can use a function phi. Now, if we have a single layer neural network or single layer perceptron, it can, the decision boundary is represented by a straight line. Suppose x1 and x2 are the two features that you have. The decision boundary is a straight line, and such units will work to represent functions where the two classes, examples belonging to two classes, can be separated by a straight line. For example, if you look at the slide, here we have two classes, class 1 denoted by red plus, class 2 denoted by blue circle, and there is a straight line function that separates them. On the right, we see two other examples where we have class 1 which is red, class 2 which is blue, and there is a line separating class 1 from class 2, and there exists a linear decision boundary which separates class 1 from class 2. Now, let us look at this fourth example in the bottom left. Here we have two red points, two red plus points, two blue 0 points. Now, these examples we cannot have a linear boundary which separates the blue points from the red points. So, such a machine learning problem cannot be represented by a single layer perceptron. Now, this is an example of a function which can be represented by a single layer perceptron, and this particular function is the Boolean OR function, which most of you are familiar with. The Boolean OR function outputs 1 if any of the inputs is 1, and outputs 0 only if all the inputs are not 1. Now, this function can be represented by a single layer perceptron, and learning the function means learning the weights on the corresponding edges. So, there are three weights associated with this perceptron: W1 from x1 to the unit, W2 from x2 to the unit, and W0 which is the bias. Now, this particular diagram shows you that some specific values of W0, W1 and W2 for which we can implement this function. This function can be implemented by some sets of values. This is an example of a set of values which can implement this function. Okay. So, this is the representation of the OR function, and given this particular values of W0, W1 and W2, we get a linear decision boundary which separates the space into two regions, so that the plus points are in one region, the minus points are in another region. Similarly, this is another example of a function which can be represented by a single layer perceptron. This is the Boolean AND function, where the output is 1 only if both the inputs are 1, otherwise the output is 0. It is represented by this diagram and this decision layer corresponding to some specific weights, right. So, for example, if I set W1 equal to 1, W2 equal to 1 and W0 equal to minus 1.5, it will denote a decision surface which works for this AND function. There could be other combinations of weights also which work for the AND function, but this is one combination of weights which implements the AND function. But when we have the XOR function, which is 1 if exactly one of the inputs is 1, and 0 if either both of them are 0 or both of them are 1. That is the XOR function, and as we can see, there is no linear decision boundary that separates the 0 points from the 1 point. So, in order to represent this function, we can go for multi-layer perceptrons. This is an example of implementation of the Boolean XOR function. So, we have initially the first layer, we have two perceptrons. The first perceptron H1 and H2, and then the second layer we have one perceptron O, and together these three units in two layers, they can represent the Boolean XOR function for certain combination of weights. For example, we can have the left unit, left H1 at the first layer to represent the OR function by putting the weights as 1, 1 and minus 0.5. We can have the second node at the first layer represent the AND function by putting the weights as 1, 1 minus 1.5, and we can have the node at the second layer implement the final XOR function by setting the weights as 1 minus 1 minus 0.5. This is one example implementation of the XOR function by using a two-layer perceptron. XOR cannot be implemented by a one-layer perceptron, but it can be represented by a two-layer perceptron function. Now, in general, if you look at multi-layer neural networks, we can say this thing about the representation capability of neural networks. If you have single layer neural networks, they have limited representation power, and as we have already discussed, they can represent linear decision surfaces, and therefore, if the examples of two classes are linearly separable, then only they can be represented by a single layer perceptron. If you have non-linear functions, you have to go for multiple layers. And as you can see, if we had only linear units, combination of linear units would be yet another linear unit. So, in order for multi-layer neural networks to represent non-linear function, it is important that the functions implemented at the individual units are non-linear. That is why we go for non-linear units, either threshold unit or sigmoid unit or tanh unit or so on. Now, when we go for multi-layer network, if we go for a two-layer network, so suppose this is the input unit and we have one hidden layer. So, in a neural network, so suppose this is the input x1, x2, xn are the inputs, and this is the output, and we can have one or more hidden layers. Suppose this is the first hidden layer comprising 3 nodes, right, and we can have connection from the input to the first layer, and we can have connection from the first layer to the second layer. So, such a network, this is a network with one hidden layer. If we take a network with one hidden layer, it is normally called a two-layer neural network. Such neural networks can represent all Boolean functions. All Boolean functions can be represented by a neural network with a single hidden layer. It is easy to see that it is possible because you may know that any Boolean function can be represented using NAND gates, using two layers of NAND gates. And I leave it for you to figure out that we can have a single layer perceptron represent the NAND function. We have earlier seen that neural network can represent a single layer perceptron can represent the AND function. You can, I leave it to you as an exercise to see that it can represent the NAND function, which is the inverse of the AND function. And by cascading 2 layers of NAND, you can represent any Boolean function, and any Boolean function can therefore be represented by a neural network with a single hidden layer. So, this is quite obvious. Secondly, we can say every bounded continuous function can be approximated with arbitrarily small error by neural network with one hidden layer. So, not just Boolean function, if you take a continuous function, if the continuous function is bounded, right, that is, it does not go to infinity, it is within a bound, then any continuous function can be approximated by arbitrarily small error using a single hidden layer neural network. But if you have a neural network with 2 hidden layers like this, so this is the first layer, this is the second layer H2, and there is a connection from the nodes in H1 to the nodes in H2, and then there is the output. So, this is called a 2 hidden layer neural network. It can be shown that any function at all can be approximated to arbitrary accuracy by a network with 2 hidden layers. If you are using a network with 2 hidden layers, such a network can represent any arbitrary function, which is a very powerful statement. However, where is the catch? Just because a given network can represent a function does not mean that the function will be learnable, in the sense that, as we will see in a neural network, we do not know. So, we say that there exists a neural network which can represent this function, but that neural network comprises of a number of nodes in the different layers and a number of weights, right. So, we know that a function can be represented by a 2 hidden layer neural network, but we do not know how many nodes we should put, what should the weights be, and we do not know how many nodes we will put. So, that to figuring out how many nodes we will put and what would be the weight may turn out to be hard for different problems. And when I said that any Boolean function can be represented by a network with one hidden layer, I did not mention anything about the number of nodes that you require. There can be some Boolean function for which the number of nodes that you require can be very large. So, just because a function is representable may not mean that it is learnable. Now, we will see how we can learn in a multi-layer neural network using the backpropagation algorithm. Now, if you look at the slide, this is the schematics of a multi-layer neural network. So, we have the inputs, we have the first hidden layer. So, this shows a 2 hidden layer neural network. The input, the yellow nodes are the first hidden layer, the blue nodes are the second hidden layer, and the green nodes are the output layer. Now, as we have earlier discussed, that when you give the input and you observe the output, and if you have a training set, the training set will tell you for a given input what should be the ideal output. And from the training set, you can find out what is the error for a neural network unit for a particular input, and we can update the weights so that this error is reduced. Now, the error is only observed at the output layer. So, if you have a neural network where this is the input layer and this is the output layer, and these are some hidden layers, and there is connectivity between this and this, this and this, this and this. For the nodes at the output layer, we can find out the error for a given input. So, if I take the first input x1, we can find out what is the output y1, and we can find out what is the output that we are getting using the neural network. So, we can find out at every node for that given input what is the actual error, and we can try to change the weights so that the error becomes small. But the error can only be observed at the output, we do not know for a training example what should be the value of a node here or a node here, right. So, what we are going to do is that the error that we find at this layer, we are going to backpropagate the error and estimate the error at the inside hidden layers. We are going to take the error which we observe at the output layer, backpropagate the error to the previous layer. So, we say that the error here is because of the error which was computed here. So, the blame of the error here partially depends on the error at this node, which in turn depends on the error at this node. So, we will take this error and backpropagate it to the other nodes from which it takes input. And if you look at the weight of this edge and the weight of this edge, if this has a higher magnitude of weight, this node has higher contribution here. If it has a smaller magnitude of weight, it has a smaller contribution here. So, when we apportion the error backwards, we apportion the error proportional to the weight. If the edge has larger weight, we put larger error, we apportion to that node. Okay. So, backpropagation works in this way. When we apply the neural network on a particular input, the input signal propagates in this way, right. Input signal gets computed in this way, so that we can get the output. But when we find the error, we find the error at this layer, and the error is backpropagated to the previous layers. And based on the notional error out after backpropagation, based on that notional error, we do the weight updating at these layers. So, here we update the weights based on the directly observed errors. After we have backpropagated the error, we find the notional error at this level, and based on that we change these weights. Again we backpropagate this error further here, and based on that we change these weights. So, that is why we call this method backpropagation. Backpropagation is a method to train multi-layer neural network. The updating of the weights of the neural network is done in such a way so that the error observed can be reduced. The error is only directly observed at the output layer. That error is backpropagated to the previous layers, and with that notional error which has been backpropagated, we do the weight update in the previous layers. Now, in the last class, we have looked at the derivation of the error, derivation of the update rule of a neural unit based on the error, right. We saw how we could use gradient descent to find out the error gradient at a unit, and we could change the error based on going to the negative of the error gradient. Just to recapitulate, if you have one output neuron, the error function is given by E equal to half y minus o whole square. For a particular input, y is the expected out, y is the gold standard output, o is the actual output. So, y minus o gives you the error. So, half y minus o whole square is the particular measure of error that you are using. Now, for each unit j, the output oj is defined as oj equal to the function phi applied on net j, where net j is the sum of the weighted sum of the units at the previous layer. So, net j is sigma wkj ok, and phi is the nonlinear function that we are using. As we have mentioned, we could use phi as a sigmoid function or tan h or ReLU or some such function, and wkj corresponds to those edges which are coming from the previous unit to this unit. The input net j to a neuron is the weighted sum of outputs ok of the previous n neurons which connect to this neuron. And following the method which we followed in the last class, now given this, we can find out, given that formula E equal to half y minus O whole square, and O is as it is defined here, we can now try to find out the derivative of this error function with respect to the different weights. So, as we have n different weights n plus 1 different weights corresponding to the previous inputs and the bias, we can take the partial derivative of this error function with respect to each weight, and this quantity partial derivative of the error function with respect to wij, which is one specific weight, can be rewritten as, by the chain rule, del E by del Oj times del Oj by del net j times del net j by del wij, right. So, net j equal to sigma wkj ok and Oj equal to phi of net j, and we can write this del E by del wij in this form. Okay. Now, so this is what we have rewritten here. This is the error function, this is Oj, and del E by del wij, this is what we did in the previous slide. Now, this can be written as del E by del Oj can be written as summation over L del E by del OL by del net ZL times WJZL, which corresponds to the this output is coming from the other outputs, other nodes which are indexed by L, and this is phi of net j into 1 minus phi of net j, which is the corresponding to the sigmoid function, and this is OI. This follows from the derivation that we worked out in the last class. So, simplifying, we can find out that del E by del wij is delta j OI, where this quantity is called delta j, right. The detailed derivation we have done in the last class. So, del E by delta wij is delta j OI, where delta j comes from the nodes of the next layer, from the errors in the next layer is back propagated to the previous layer, where delta j is given by del E by del Oj by del net j, which is equal to Oj minus Yj into Oj times 1 minus Oj if j is an output neuron, if I am at the last layer. Otherwise, it is recursively computed as sigma over z delta zl wjl times Oj times 1 minus Oj if j is a neuron in the hidden layer. Okay. So, delta j can be computed directly at the output layer, and once you have computed delta for each of the output units, you can compute delta of the previous unit. After you have computed all the deltas of the previous unit, you can compute the delta of the previous to previous unit. So, that is called the back propagation, and based on that, this is the recursive computation of delta starting from the last or the output layer and going one level backward up to the beginning. So, now once you have figured this out, you know what is del E by del wij, and then you change the weights using gradient descent, delta wij equal to minus eta del E by del wij, right. So, this is the gradient, this eta is the learning factor, small eta means slow convergence, large eta means faster rate, and minus because we are doing gradient descent. So, based on this, we can write the back propagation algorithm, which is actually very simple as is given in this slide. We take a neural network, we have a structure, we have one hidden layer or two hidden layer, whatever you want. You decide the number of layers in the neural network, number of units in each layer, and you do connection from the input to the first hidden layer, first to the second, second to the output, and then you have a number of weights. Initially, you initialize all the weights to small random numbers. After that you carry out an iterative process which is given as here. Until satisfied, what you do is you input, you have a set of training examples, you input the first training example to the network and compute the network output. So, you give x, you find y. Now, for each you find O, you give x1, you find O1, you give x2, you find O2. Now, for each output unit k, you may have only one output or multiple outputs. For each output unit k, you compute delta k at the output layer as OK into 1 minus OK into yk minus OK. Then you go to the previous hidden layer. For each hidden unit h, you compute delta h as equal to OH into 1 minus OH into sigma over WHK delta k for all k which are in the outputs. Now, after that you update each network weight Wij as Wij is Wij plus delta Wij and delta Wij is minus eta delta j Xij as we have already seen. So, this is the back propagation algorithm. We have an input, we have the output that we get from the network, and we have the target output. We find the error from the target output. Based on that, we update the weights, we back propagate the weights to the previous layer by propagating the delta value and continue. We continue for all the hidden layers. So, this is the back propagation algorithm, but it is very simple to implement. So, in back propagation, we do gradient descent over the network weight vector. And even though the example we have shown is for a layered graph, we can do back propagation over any directed acyclic graph. The second thing to observe is that by doing back propagation, we are not guaranteed to find the global best. We only get a local minima. So, we have a very complex error surface comprising of the weights at all the layers. By doing back propagation, we are updating the weights to do better and better, and we continue doing it until the network converges. But when the network converges, it will converge to a local minima which need not be a global minima. And there are certain tricks that one can use to prevent getting trapped in a local minima. For example, one such trick is to include a momentum factor called alpha. So, the idea is that if you are going and trying to hit a local minima, you try to prevent that by maintaining the previous direction of movement, by the general direction of movement. You do not want to deviate and get stuck. So, momentum, what it does is that when you change delta Wij, you not only look at eta delta xj xij, which we had derived earlier, but we also keep another factor which keeps track of the direction of weight change at the previous iteration. Delta Wijn is the weight change at the nth iteration, which is equal to eta delta j xij plus alpha times direction of weight change in the previous iteration. If you apply the momentum, training may be a slow, but you are less likely to hit a local minima or bad local minima. But one thing to note is that in neural network, when you use multiple layers, even if training is slow, after you have learned the weights, applying the neural network is very fast. Now, there are a few other observations I will make. When we do the weight update, we can do a batch update. That is, given a particular configuration and given a set of training examples, with respect to all the training examples, we can compute the partial derivative of the error and find the best way of updating it. Or we can do it for one input at a time. So, the first method is called batch gradient descent. The second method is called a stochastic gradient descent, where you take one input at a time. Based on that, you change the weights. Now, stochastic gradient descent is less likely to get stuck in a local minima, because if there is a local minima, it is unlikely that for all examples it will be that minimum. So, first if you use stochastic gradient descent, the neural network is more likely to get towards the global minima. And there is something in between which is called mini batch gradient descent. So, instead of taking all the examples at a time or a single example at a time, you take a batch of examples at a time, and with respect to that you do gradient descent. So, batch gradient descent calculates outputs for the entire data set, accumulates the errors, then backpropagate and makes a single update. It is too slow to converge and it may get stuck in local minima. Stochastic or online gradient descent, on the other hand, will take one training example at a time. With respect to that, it will find the error gradient. It converges to solution faster and often helps get the system out of local minima. And in between we have mini batch gradient descent. Now, the entire training process can be divided into epochs. If you have a number of training examples, one epoch will look at all the training examples once, then we will have the second epoch, then the third epoch, etc. So, when you are learning in epochs, when do you stop? So, we keep training the neural network on the entire training set over and over again, and each episode is called an epoch. And we can stop where the training error is getting a saturation, or we can use cross validation. While we are training the neural network, we can also keep validating it on a held out set. And when we see that the training and validation errors are close, then we can stop. Or we can stop when we reach a maximum number of epochs. Now, in neural networks, like other machine learning algorithms, overfitting can occur, and this overfitting is illustrated by this diagram. So, on the x-axis we have the number of iterations, and the y-axis we have root mean square error. As is typical of many machine learning algorithms, as we increase the number of iteration, the error on the training set keeps on reducing, and it may even become 0, may or may not become 0. But the error on a held out set typically will initially decrease and then it will increase when overfitting has occurred, right. So, this is the zone where overfitting has occurred. Ideally, you should stop before the validation error starts to increase. So, if you can keep track of the validation error, you will know that this is the place where you must stop and not continue any more iteration, because beyond that the network is likely to overfit and the accuracy of the network will go down. So, this picture illustrates local minima. As we said, neural networks can get stuck in local minima for small networks, and we also said that if you use stochastic gradient descent, it is less likely to get stuck in local minima. But in practice, when you have a large network with many weights, local minima is not so common, because we have so many weights. It is unlikely that, and you are doing every weight separately, it is unlikely that the same local minima will be the minima of all the weights. So, in conclusion, we can say that artificial neural network lets you use highly expressive non-linear function that can represent almost all functions. It comprises of a parallel network of logistic function units, or other types of units are also possible. The principle works by minimizing the sum of squared training errors. There are also neural networks with different other loss functions, but we will not talk about it in this class. Here we have looked at neural networks to minimize the root mean square error. We can add a regularization term to a neural network, which I did not talk about. So, what you can do is that you can try to prevent the weights from getting large by penalizing networks where the weights have large values by adding a regularization term. Neural networks can get stuck in a local minima and it may exhibit overfitting. So, with this we come to a conclusion. In the next class, we will give a very brief introduction on deep learning. Thank you very much.